Alrighty, continuing on, we're now doing lesson 5, top-down LL parsing. I've already done my Anki for the day. I suggest you do yours too. Don't be lazy. Yeah, let's get into it. Top-down LL parsing. We saw that previously we could build a recursive descent parser for S expressions, implementing parsing of the following grammar. S can equal some terminal X, or it can equal this non-terminal L inside brackets, and L can equal the empty string or S concatenated with itself. Recall that the symbols X are all terminal symbols, where X stands for any legal identifier, brackets terminal symbols, obviously. Predictive parsing table. The recursive descent parser code can be abstracted into a table that describes its functions succinctly. The predictive parsing table, PPT. The core task of a top-down parser is to use the next input token to predict which production to use, assuming that the upcoming input is expected to correspond to a given non-terminal. For example, the recursive descent parser for S expressions can be summarized in the following PPT. Okay, so so I guess if we see a bracket, that means we could be inside S, we could be inside L. I think that's how it's working. And if we see X, then we could be inside X, or we could be seeing the L non-terminal. If we see this closing parentheses, then how does this work? Each row of this table corresponds to different cases found inside a single parsing function in a recursive descent parser. Each column corresponds to a different input token, where the $ represents the end of the input. Alternatively, it is possible to build a non-recursive parser whose actions are driven by a PPT. Right, so a recursive descent parser is a parser that's top-down. So we start at the top of the context-free grammar, and then we build our syntax tree from the top, and we expand the top all the way until we get to the bottom, and all we have left is terminals. So from memory, these things, they actually implement these are called productions. They implement these productions as functions from memory. So if we're in the S function and we come across an opening parentheses, that means we're in this form of the production. If we're running the S function and we find this token, then that means we've just hit a terminal. If we run the X function and we find the closing parentheses, something's wrong. Go into an error state. If we run the L function and we find an opening parentheses, okay, yeah, I get it now. If we run the L function and we find the closing parentheses, we are at the empty string. Okay. Table above is a one look ahead predictive parsing table. It is also possible to have a PPT that looks ahead more than one symbol. For example, a 2 look ahead PPT would in principle have a column for every possible combination of 2 input tokens. Okay. In practice, we want to use a more efficient representation. Since the table is typically quite sparse, and in a K look ahead table, the number of columns will be O to the power of the size of the alphabet to the power of K, where K is a set of non-terminals. We say that a grammar LLK if a K look ahead. We say that a grammar is LL of K if a K look ahead PPT can be constructed. In particular, each cell in the predictive parsing table must contain at most one production, with the implication that the parser knows what to do in that case. Okay. I'm not 100% sure I want to remember this too bad. Like, I mean, it makes sense if I see a predictive parsing table. I can, now that I know what a context-free grammar is and whatnot, I could decipher it again in the future, I'm sure. Table-driven top-down parsing. A predictive parsing table can be converted fairly directly into a recursive descent parser. It is also possible to construct a table-driven parser that is not recursive. The table-driven parser maintains a stack of items that represent partially completed parts of the derivation. Partially completed parts of the derivation. An item consists of a production from the grammar with a dot inserted somewhere into the right-hand side of the production. Everything to the left of the dot corresponds to input that has already been read. Everything to the right of the dot represents input that has not been read yet. For example, S is this would be an item representing the partially derived non-terminal S where the left parentheses has already been read and input derived from the non-terminal L is expected next, followed by a right parentheses. Okay? Given such a stack, the table-driven parser proceeds as follows. Taking one of three actions based on the item currently at the top of the stack. Taking one of three actions based on the item currently at the top of the stack. We can scan if the dot is to the left of a terminal symbol, an input token is read. If it matches the expected terminal, the dot is advanced to the right by one position. Otherwise, a syntax error has been detected. Predict. If the dot is to the left of a non-terminal symbol, the predictive parsing table and the current look-ahead symbol are used to look up the expected production. This production is then pushed onto the stack as an item with its dot at the leftmost position. And complete. If the dot is at the right hand side of the production, the item is complete. The item is popped from the stack and the dot in the new top of the stack is advanced by one position. This is the point at which some action would be performed, such as constructing an abstract syntax table node corresponding to the completed production. Okay, alright. To start the parser, the stack is populated with an item that is looked up in the predictive parsing table using the start symbol and the initial look ahead, the first input token. The dot in that item is in the leftmost position. For example, to parse the string A within parentheses, the parser goes through the following states. The stack is shown growing downward, so its top is at the bottom. So we start, we haven't read anything, so our dot is on the far left. We scan in the next token, it's a non-terminal, so when we scan, if the dot is to the left of a terminal symbol, an input token is read. If it matches the expected terminal, the dot is advanced to the right by one position. So we scan, we read in a terminal, which is open parentheses. So it's all good. So we move the dot to the next space. Next. Wait, why are we predicting? Next we predict if the dot is to the left of an, if the dot is to the left of a non-terminal symbol. Oh, okay, yeah. So if the next symbol is non-terminal, which it is, it's L, the PPT and the current look-ahead symbol are used to look up the expected production. This production is then pushed onto the stack as an item with its dot at the leftmost position. So then we check L, so we would expect the next production to be whatever the next rule is, SL or an empty string. Predict again on S. S can be equal to X. We find the terminal X, so therefore we move our dot to the right. Then we pop that from the stack, so we complete it. Pop it from the stack, put it into our abstract syntax tree, do whatever we do there. Then we check the next non-terminal. So that'll be L. We pop that onto the stack. We find the empty string. So we can pop that from the stack by completing it and put that in our abstract syntax tree. Then we're done with this production, so we can pop that from the stack by completing it. Yeah, pretty simple. And then we have to scan. Since we're not to the left of a non-terminal anymore, we can just scan terminals in. Makes sense? Note that the 7th step, the dot is immediately at the end of the top stack production, since the right hand side of that production is the empty string. Yeah, I did notice that we immediately move past the empty string, because yeah, let me check that. If the dot is at the right hand side of the reduction, now it's complete. Note that at the 7th step, 1, 2, 3, 4, 5, 6, 7 here. Oh, yeah, definitely here. The dot is immediately at the end of the top of stack production, since the right hand side of that production is empty. Okay, so we can just, yeah, we move past the empty string. Okay, nullable. To build the PPT, some facts must be computed about the grammar. For simplicity, we consider only the LL1 case. Recall that we use Greek letters, for example, alpha, beta, and whatever the hell that is, I can't remember it right now, to represent a sequence of terminal and non-terminal symbols, including an empty sequence, and that the symbol eta represents the empty string. I think that's eta. The first fact we need about the grammar is whether each non-terminal can derive the empty string. We compute a predicate nullable x, which is true exactly when there is a way to derive the empty string from x. Okay. Given a definition of nullable x, we can determine whether an arbitrary string beta is nullable. If beta contains any terminal symbols, it's not nullable. If beta is some string a1, a2 to an, where n is greater than 0, then beta is nullable if all of the a sub i's are nullable. The algorithm works as follows. Set nullable x to false for all non-terminals x. 2. Repeat the following step until no more changes to nullable x are possible. Find some non-terminal x that has a production x. X is, what is that? What is this symbol? I need to look it up. Gamma. There we go. X is gamma, where gamma is nullable given the current values for the predicate nullable, and set nullable x to true. For example, consider the S expression grammar. The algorithm converges on the correct value of nullable after one iteration. Iteration 0, nullable S, nullable L. So if L is nullable, wait, what? More generally, the algorithm works because nullable X only changes in the direction from false to true. It is only set to true when the algorithm has proved that X is nullable. The algorithm can only take as many iterations as there are non-terminals in the grammar. Since on each iteration, one non-terminal is marked as nullable. When the algorithm terminates, it has found all the nullable non-terminals. This can be seen by induction on the number of steps in the derivation of the empty string for each non-terminal. Alright. I am completely lost. To build the PPT, some facts must be computed about the grammar. For simplicity, we consider only the LL1 case. What were we saying about LLK up here? We say that a grammar is LLK if a K look-ahead PPT can be constructed. Right. So this is a 1LL PPT. Recall that we use Greek letters alpha, beta, gamma to represent a sequence of terminal and non-terminal symbols. The fact that we need about the grammar is whether each non-terminal can derive the empty string. Okay, so we're trying to derive the empty string. We compute a predicate nullable X, which is true exactly when there is a way to derive the empty string from X. Given the definition of nullable X, we can determine whether an arbitrary string is nullable if it contains any terminal symbols. It's not nullable if beta is some string, and B is nullable if all of A sub I are nullable. The algorithm was set nullable to false for all non-terminals X. So iteration 0, everything's set to false. Repeat the following step until no more changes to nullable X are possible. Find some non-terminal X that has a production X to gamma, where gamma is nullable given the current values for the predicate nullable. Set nullable to true. The algorithm converges on the correct value of nullable after one iteration because we can derive the empty string from L. So we start by assuming they're all not nullable. Then we eventually get to L, which can derive the empty string. Does that mean S is also nullable because S can contain L? No, S can only contain I'm not sure. I guess we'll find out. More generally, the algorithm works because nullable X only changes in the direction from false to true and is only set to true when the algorithm has proved that X is nullable. The algorithm can only take as many iterations as there are non-terminals in the grammar, okay? Since on each iteration one non-terminal is marked as nullable, therefore the algorithm always terminates. When the algorithm terminates, it has found all the nullable non-terminals. This can be seen by induction on the number of steps in the derivation of empty string for each non-terminal. Okay, so I mean, I guess it makes sense to So if you want to find out if the empty string can be derived from S, you need to find a path from S that can get to the empty string. And I don't think we can, because while we can get to L, which can be empty string, I don't think we can get explicitly to L without brackets. So therefore S can't be the empty string, I think. First, recall a top-down parser needs to predict productions based on the first symbol it sees in the derivation using that. Recall a top-down parser needs to predict productions based on the first symbol it sees in the derivation using that production. Therefore, it is useful to compute the symbols that can begin the expanded form of non-terminals. Therefore, it is useful to compute the symbols that can begin the expanded form of non-terminals. We write first x to represent the set of terminals that can begin a string derived starting from x. Makes sense. This function, once known, can be extended to operate on arbitrary strings, gamma, as follows. So first, for the empty string, there are no strings, so there is nothing that can begin the empty string. First of A beta is the set containing A. First of A beta, so this is some non-terminal A beta equals the first of A if A is not nullable. Okay. First alpha beta, it was first of A unioned with the first of B if A is nullable. Okay, where are we going with this? Since the strings derived from non-terminal X must come from one of its productions, the following equation must hold for each non-terminal X. The first of X is the union of the set containing the first of gamma or X, what? X derives, X is gamma. The union of X derives gamma concatenated with the first of gamma. I'm gonna try and see if ChatGPT can parse this, because I'm super confused. What does this mean? The notation first X refers to the set of terminal symbols that can appear as the first symbol of a string. Okay, yep. In other words, it represents a set of terminals that can begin a derivation of strings from the non-terminal X. What does that mean? The set of terminals that can begin a derivation? I don't understand what that means. That can begin, as in like the first letter. Right, yeah, okay, yeah. The equation you provided defines first X in terms of the productions of non-terminal X. X produces gamma in a production. X produces gamma in a production is a production of X. Here the set represents the union operation and the notation first gamma X produces Y F produces. Gamma in a production denotes the set of first gamma for all productions of the non-terminal X. So the equation is saying that the set of terminals that can appear as the first symbol of a string derived from X is the union of the sets of terminals that can appear as the first symbol of each alternative string in the productions of X. In simpler terms, first X includes all terminals that can begin strings derived from X based on the productions of X. This concept is often used okay. I mean, I roughly get it, but I'm not going to say I fully understand this. Since the strings derived from non-terminal X must come from one of its productions, the following equation must hold for each non-terminal X. Note that the second line is just an alternative notation for taking a union. To solve these equations for a grammar G, we use an approach similar to the computation of nullable. Set first X equals, I can't remember what that symbol means. I think it's like, I can't remember what that means. Repeat the following step until no change is possible. Apply all first X equations as assignments, updating first X to be the union of first gamma, or X derives gamma in a production, X produces gamma in a production, as in the set of G. For example, consider the computation of first for the S expression grammar. Expanding and simplifying equations, we have first of L equals the first of SL union of the first of empty string equals the first of SL equals the first of S. First of S equals the first of L within brackets unioned with the first of X okay. Oh, okay, I see it. Yep, okay. So we eventually get down to this union here, which is the first of this string, because there's a terminal at the start of it, and there's also a terminal here. So the first of a terminal is whatever's the first of the terminal. Cool. Okay. Now we can apply these equations using the algorithm above to find solutions iteratively. First of S because the first of L is equal to the first of S on the second step. The algorithm works for much the same reason that the algorithm for computing nullable does. At each iteration, the value of first X is a conservative approximation of the true value. Nothing is ever put into a first set that does not belong there. The algorithm must terminate because first sets only increase in size at each iteration, and they can't keep growing forever. When it does terminate, it therefore finds the minimal solution to the equations. We'll see later that both of these algorithms and others are instances of the fixed point theorem, a set of equations that can be solved in this iterative fashion when they satisfy certain conditions. Cool. What is the fixed point theorem? Is a result saying that at least one fixed point exists under some general condition. A fixed point is also known as an invariant point. Is a value that does not change under a given transformation. Specifically for functions, a fixed point is an element that is mapped to itself. Okay. Alright. A set of equations can be solved in iterative fashion when they satisfy certain conditions. Cool. Alright. Follow. All of the cells in the S expression PPT are now explained by first, except for one, the cell for non-terminal L with look ahead closing parentheses, where the parser is supposed to predict the production L produces empty string in a production. This production is chosen because the symbol closing brackets can follow the derivation of L somewhere in a string derived from the start symbol S. In general, we will need to know what set of terminals can follow a non-terminal X. We call this set follow X, where in general we need to know what set of terminals can follow a non-terminal X. There are three sources of symbols in this set. If X appears on the right hand side of production, Y, X, beta, then any symbol in first beta is in follow X. Yep. If X appears in a production and beta is nullable, then any symbol in follow Y is also in follow X. Okay. I don't quite understand that. So if X appears in a production there and B is nullable, any symbol in follow Y is also in follow X. Okay, alright. If X is the start symbol of the grammar, then the special end of input symbol is in follow X. Okay. These three sources can be interpreted as the basis of an equation for defining follow X as equal to the union of three sets. Call that A and beta can stand for empty sequences. Expand these equations. For example, grammar we have follow S equals first of L union with follow of L union with the ending, the end of input symbol equals follow L unioned with these terminals. Follow L equals first of this unioned with follow L unioned with nothing. So follow L equals follow L unioned with closing parentheses. These equations can be solved iteratively, just like those for the nullable and first. Initialize follow X equals nothing for all X. apply the equations for follow x repeatedly as assignments, using the current value of follow x to interpret the right hand side of each equation until no further change occurs. First iteration follows s is nothing. Sorry, 0th iteration. First iteration, what follows s is this set here. What follows L is this. Then we include whatever's in follow L within follow S. Notice that because follow L appears on both the left and right hand sides of this equation, other solutions to the equations could be found. However, the iterative solving technique produces the smallest set satisfying the equations. Okay, so we have nullable, we have first, we have follow. Constructing the predictive parsing table. Using the first and follow sets for the various non-terminals is straightforward to build the predictive parsing table. A production x produces a gamma in a production is placed into the predictive parsing table cell for a non-terminal x and a terminal under two conditions. If A is in the set of first of gamma, and if A is in the set of follow of x and gamma is nullable. Applying these rules to the S expression grammar, we obtain the PPT given at the beginning. If each cell contains at most one production, then the grammar is LL1 and can be parsed by a recursive descent parser. If a cell XA contains no production, the parser detects a syntax error whenever it is parsing an X and sees the terminal symbol A. If a cell contains two or more productions, the grammar cannot be parsed with only one look-ahead token. If a cell contains two or more productions, the grammar cannot be parsed with only one look-ahead token. It is not LL1. Either the grammar must be rewritten into a more powerful parsing. It must be rewritten, or a more powerful parsing technology is needed. Fixing grammars to be LL1. We've already discussed how to change grammars to be unambiguous for some common cases. However, even unambiguous grammars can fail to be LL1. One common problem is that two productions from a given non-terminal can have overlapping first sets. For example, if the grammar contains productions S to E and S to E plus S, clearly first E and first E plus S are not disjoint. If the grammar contains productions S to E and S to E plus S, clearly first E and first E plus S are not disjoint. Makes sense. The solution to this problem is often left factoring. We introduce a new non-terminal that captures the part of the productions is not in common. So this becomes this after the introduction of new non-terminal T, compatible with LL parsing. Okay. Another problem that commonly arises is left associativity, which is naturally expressed using left recursive productions. Left recursive productions automatically cause conflicts among first sets, however. A common useful trick is to rewrite left recursive production into right recursive form and then to fix the associativity in the step where the parse tree is converted into the abstract syntax tree. For example, suppose that we have the grammar. S drives, F produces E or S plus E. We can write a right recursive grammar that accepts the same language but generates a right associative parse tree. S produces E or E plus S. Abusing regular expression syntax, we could also write a grammar that uses clean star to achieve the same effect. The parentheses and asterisks are meta syntax here. E concatenated with plus 0 or more instances of plus E. This grammar suggests that we can parse non-terminal S using a loop instead of recursion along the following lines. Void parse S. Can we parse E while peak equals plus, scan plus, then parse E. By extending this code appropriately, we can construct an abstract syntax tree with whatever associativity is desired. We can construct an abstract syntax tree with whatever associativity is desired. In particular, it is easy to construct a left associative abstract syntax tree. While the next token is plus, scan plus, result equals new plus, result, and parse E. Okay, I'm thoroughly confused, and I need to see, probably need to see some actual like examples of this. So the Dragon book, they recommend looking at the Dragon book. Let's see what the slides look like. Where we are, source code, character stream. So we have a token stream, we want to build an abstract syntax tree. This might help a bit. So if we have this grammar, some number or S in parentheses, construct a leftmost derivation of a string while reading in token stream. So if we start at the top and look ahead is parentheses, we have to get all the way down here to the parentheses. So to do that, we have to go into E. We could be E plus S, so we go into E, look ahead is still this, then we find this non-terminal, or this production, substitute it in. So again, we can go into S. S can be E plus S. Then we find, in E we find some number, plus S. Do this again. Sorry, right, a look ahead changes. That's where we find it. Okay, so look ahead becomes 1. Find E plus S. E, we have a number, so we can say we've parsed 1. S again, our look ahead is now 2. So we go into E again, find number 2. So on, we get to S, plus 2, plus E, because the look ahead changes to parentheses. Problem, we want to decide which reduction to apply based on the next symbol. S to E to S to E within brackets to 1 within brackets. Why is this hard? This grammar cannot be passed top down with only a single look ahead symbol. So we now have a new grammar. S prime, empty string or plus S. So we see S, our look at is this. We go into ES prime, look at is still this. Well, S prime, oh, an E is a number or this. So we have to go into E. It has to be this S. And then our next look ahead is 1. And we're on S, so we have to go into S. We have to look for E is a number, 1. Then we're left with S prime. It can either be an empty string or plus S. we get a plus. Wait. Next lookup symbol is a plus. S prime can be an empty string or plus S. Wait, what do you do at this point when you have to go into S prime? S prime can expand I don't see how S prime can, wait, S prime can become, what? Oh, okay, so S prime becomes this plus S, which then becomes ES prime again. So they did 2 steps there. Then I look at this symbol is 2. We can put a 2 there. S prime is a plus. S prime can become plus S, which can then become S prime S, yep. S, now we have a parentheses. So S can become ES prime parentheses is our lookup symbol, therefore we can go back to S in parentheses. That's fine, then we expand it out to ES prime again because S becomes ES prime. Place a 3 there because we have E goes to the number. S prime can become plus S. Plus, that doesn't seem right. Plus S prime can become plus S, which can become plus ES prime. Not sure about that last step. I don't understand that last step, how you get to E from S prime. So S prime, yeah, I'm not sure. Okay, so using a table probably makes it more simple. So if you have, you're in the S production, your lookup is open parentheses, becomes ES prime. Then you're in the you're in E, open parentheses becomes S. Yeah, no, it's a lot easier with the table. Cool. So you have 3 functions, parse S prime, parse E. Based on the token, lookout token. If it's a number, you do parse E, then parse S prime, return. if it's open parentheses, parse E, parse S prime, return default, throw new, parse error. So this is parse S. Cool. Okay, this is starting to piece together now. Starting to actually make sense. Wish I could have seen the lectures for this one. Would have helped a lot. So this is 5, isn't it? 5 top down LL parsing. I'm gonna add some stuff to Anki. Predictive parsing table, not a tree. So yeah, like how do you, what is a PPT used for? Used by recursive descent parsers. Parsers to done inside each yeah, so it's used by recursive descent parsers to describe exactly what should be done inside each function or production when it encounters a certain lookup token. Okay, it's slowly coming together. Slowly making sense of this. So, constructing parsing tables, that was the bit that really stumped me, I think. Can construct a predictive parser if every non-terminal, every lookahead symbol can be handled by at most one production. Here we go. So, follow X for a non-terminal. X is a set of symbols that might follow the derivation of X in the input stream. If gamma can derive an empty string, gamma is nullable. Add gamma for each symbol in follow X. Grammar is LL1 if no conflicting entries. Completing the parser. Now we know how to construct a recursive descent parser for an LL1 grammar. LK generalizes this to K lookahead tokens. Now we know how to construct a recursive descent parser for an LL1 grammar. Creating the AST class add extends expression. AST representation, how to generate this structure during recursive descent parsing. Okay, I mostly understand actually constructing the PPT is definitely tricky for me. So the first, I guess I just need to see it, the method be done. Let's see if there's anything on YouTube actually. Construct a predicted parsing table.
Hello everyone and welcome back. In this session,
Actually, you guys won't be able to hear this, so I'm just going to end the video here. It's pretty much bedtime anyway, but we'll hit it again in the next episode. Thanks for watching.